So the eventual goal here is, wouldn't it be nice? Wouldn't it be nice to think about a circular motion in 3 dimensions where the circle had been angled somehow? That's going to be the goal of this. And it's going to be just a hopefully fairly simple variation on something familiar already. So here we go. So the familiar thing, if we're in 2 dimensions and you want a circular motion, we know what that looks like. That's cosine t sine t. I want to show you a different way of thinking about the meaning of why this makes a circle. And that way of thinking is going to lead into this other, more powerful way of making circular motion. So let's think about 1, 0. 1, 0 is a vector that just length 1, it sits to the right. If I scale it by 2, now it's twice as long to the right. If I scale it by -2, now it's twice as long to the left. So what would happen if I have my vector and I scale it by cosine t? If you imagine as time goes on, this value is oscillating between +1 and -1. And if you imagine that that number is telling us how much we're scaling this vector, it's like at times 0, our vector's a dot, and then, well, I guess it's cosine. So at times 0, cosine is 1, so our vector is length 1. As time increases, the value of cosine goes towards 0. So as time increases, my vector is going to get shorter and shorter to nothing. Then it's going to go in the opposite direction. Then it's going to get shorter, shorter to nothing. So what this is going to end up with is this kind of slowly oscillating back and forth vector. I'm going to pause. So here's the video. This green dot, let's speed this up a little bit. Okay, so this green dot is the end of the vector, and you can see it just oscillating back and forth. And here is the equation that we were just talking about, the vector 1, 0, but being scaled by cosine. Okay, so let's stop that. Let's have the vector 0, 1. So show me, what direction does that face? Straight up. And let's scale that vector by sine of t. So it's going to be the same thing. It's being scaled by a number that's oscillating. But remember, sine and cosine are kind of shifted away from each other. So their oscillations are kind of opposite of each other in a certain sense. So here's what they both look like together, which is like really satisfying in my opinion. So here's the last bit, and we're going to slow it down for this last bit. Remember what happens when you add 2 vectors together. When you add 2 vectors together, it's like you're adding the arrows tail to tip, or tip to tail, or whatever. So here, let's pause it, and I'll show you. So here in the paused video, this is one of the vectors. This is the other vector. If I add them together, I'll just draw this vertical one at the end of that one, and it takes me to that point. And so now I want you to imagine that the arrows are there as I press play. So hopefully you can see that this very clearly circular motion, at any given time, its position we're just getting by adding these 2 oscillating things together to get the thing that's moving in a circle.
If you follow the dot, you can see it's always the same height as the line, always the same. Like it's hovering over the root.
Yeah, well said. If we didn't hear it in the video, if you follow the dot, you can see that the dot's x-coordinate is always the same as the green. And the dot's y-coordinate is always the same as the blue, the circular rotating one. So what's the point of this? The point of this is you can think about circular motion as adding together vectors at right angles that are being oscillated, or that are being scaled by oscillations that are opposite of each other. And so that's the kind of key insight that will let us make a 3-dimensional one. Down here at the bottom, you don't have the sheet of paper, but down here at the bottom, let's just imagine this real quick. So let's take 2 other vectors and apply that same idea of oscillating them. So imagine where those 2 vectors are. Convince yourself that they are right angles. So here's 1, -1, looks like this. Here is 2, 2, looks like this. Those are right angles. imagine with your neighbors, what happens if this point is oscillating back and forth, this point is oscillating back and forth, and we're going to add them together? The good news is you don't have to imagine. We can just do it. So what did I say? 1, -1, and then 2, 2, right? So let's go backwards a little bit. And can you tell what shape it is? It is an oval. Let's, there it is. So a nice way of thinking about what's happening here, just a second ago we said that the oscillating dots were like the x and y coordinates, right? Let's draw in the two directions of oscillation. We've got this way and we've got this way. So you can imagine this is a tilted axis system. So like you could imagine this is a tilted x and a tilted y, and now as it's going around, it's like it's always got the same xy coordinates as the moving vectors, but just in this tilted system. Okay, so that's 2 dimensions. Now let's think for 3 dimensions. If we want, where's my piece of paper? Aha! So if we want a circle that's moving around like this, I'm not going to actually do the equation for you because that's going to be your job. But I'm going to make a sort of a suggestion. So you saw that you can make any 2 vectors at right angles, oscillate, like scale them by oscillating scale factors, and that's going to create a sort of circular motion where your original 2 vectors are like the axes. So if you want a circular motion in 3 dimensions, imagine what are the axes? We've got this vector and this vector. Can you describe these 2 vectors? Well, these are just 2 linear vectors, so you should be able to just think about what's the xyz coordinate that it's pointing at, what's the xyz coordinate that it's pointing at. You take each one, scale it by an oscillating scale factor, and now you've created your motion.